Okay, let's talk about power series. What is a power series? Well, it's something of the form. It looks like an infinite series, but it has an x to the n in it. So something like you could have 0 or 1 to infinity. And again, if you work this out, it would just be c naught plus c1x plus c2x squared plus c3x cubed, etc. Right? And so you can think of this as an infinite series with an x to the n in it, or with a variable in it, basically with an x in it. You could also think of this as something like an infinite polynomial. So polynomials, we generally think of like a quadratic polynomial or a cubic polynomial or something like that, where the biggest term is an x squared or x cubed. And this is something where it may not have a biggest term. And it turns out this is also a useful way to think about it, about these things, because there's somehow generalizations of standard polynomials. You may also ask, like, why do we care about this stuff, these? And it's going to turn out sort of, you think about this, it's really like a function. You know, I could say f of x is this, it's a function. And it may extend, anything that extends our definition of what the possible functions that exist. So it basically gives more possible functions, because we already have all of our functions, like, you know, like regular polynomials, like sines and cosines, like exponential functions, logarithmic functions. So these are also functions, but it turns out surprisingly they sort of contain actually all possible, all the functions that we know can be written actually as power series, which we'll see later. That's the whole Taylor series idea. But even more, we can define other functions that have this. It just lets us, there are these functions that show up in math. There's like things, there's examples of functions that show up in math that are given by power series. And they're important functions, and they're not written in any simpler way. So these are some of the reasons why. This is what it is, and this is one of the reasons why we like it. Just as an example, I mean, there's lots of examples, but a fairly classic example is this one, which we've actually already seen, if you think about it. It's just the geometric series, right? It's this thing. So, so here, C sub n is 1 everywhere for all n. And this is a nice example for a couple of reasons. It illustrates a few things about power series. So first off, there's a big question about power series is, given a specific power series, for what values of x does a given power series converge? Right? It's sort of a function, but like it's almost like, what's the domain of the function? Like, what numbers can you plug in for x and actually get a finite value out of it? And that's a thing we're definitely going to want to ask. Right. So in this example, in the geometric series example, we've seen in this example, we've seen that that the series converges. We've seen that the sum x to the n from 0 to infinity converges precisely if x is between -1 and 1. So when x is greater than -1, less than 1, you could also say this as or absolute value of x is less than 1, right? And it diverges otherwise. So this thing right here is called, this right here is called the interval of convergence of this power series. Again, I'm just using geometric series facts to claim it here. And in general, we're going to want to ask, what's the interval of convergence? Now, the one thing I should say here is, if we can, I give this as a geometric representation also, that like, here's the number line, and here's 0 and 1 and -1. And I guess what we're saying is this example converges not at -1, but then sort of everywhere between -1 and 1, and then not at 1, right? So that's the interval of a convergence. We should notice that this series converges sort of this. If I go back up to this example, it sort of obviously converges for x equals 0. That's sort of the one value where it obviously converges. I always put the word obvious in quotes because things aren't always obvious. But if you think about it for a minute, if I just plug in 0 for x, right, like all these terms go away right here. All these terms just go to 0, and so the series just equals 1, right? And so this is actually called the center of convergence. And so the center of convergence, if I go back down to this picture of the number line, is right here. That's the center. And you might notice that the series converges sort of equidistant from the center, and that's going to actually be a general thing. So it converges 1 unit away from the center, left and right. And actually, maybe I'll draw it like this, just as like an arrow or something. Like it obviously converges at 0, and then it converges all the way out to 1 and -1. And so this distance is called the radius of convergence. And we'll see in our examples that these power series always have a radius of convergence and an interval of convergence. So notice the radius tells us most of the information. We know it converges at 0, that's the center. The radius being 1 means it's going to converge from -1 to 1. But we still don't know the endpoints unless we do some more analysis. And we've already done that analysis for geometric series. But in general, you'd have to do some analysis to figure out whether it actually converges at the endpoints or not. And I'll show examples of both where, it can converge at one or both or neither endpoint. And I'll get into some examples in future videos. But for now, let's just think about this. Let me just write down a couple more examples, because the thing is, like, I said it's something of the, if I go all the way back to the beginning, I said power series is of this form, but these examples also always converge. The center of convergence of all of these is always x equals 0. But what if I want something that converges somewhere else? Like, what if I want a power series that I know converges at x equals 5 instead of x equals 0? What if I want that to be the center of convergence? So can we make the center of convergence something else? Some other number besides 0? And the answer is yes. For example, if you want the center to be x equals 5, you could just do something like the following. For example, I could just put something like x minus 5 to the n right here. It's a little strange because it's a little stranger looking polynomial now. It's a little more complicated looking, and you're tempted to just kind of multiply this out. But I don't want to actually do that. We want to actually let it sit here. We want to actually put everything in terms of x minus 5. And so now the center, as you can guess, is x equals 5, right? Because if we plug in this, again, this sort of obviously converges at x equals 5. So that's the center. X equals 5 is the center of convergence. Okay. So that's another, so I should say this is another kind of way a power series can look. It's not just x to the n, it could be x minus a constant to the n. And there can even be slightly more complicated versions. It doesn't have to actually have every power. I mean, we could have something, just maybe one last example, basic example before I move on to some more thorough analysis, is what if you had some, here's it turns out is a famous power series, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. And you could think, okay, well, this is, it's only the odd power. You hopefully see the pattern. It's only the odd powers of x. So you can think of, well, the coefficient of x squared is 0, and the coefficient of x to the 4th is 0. But how would we want to write that actually in summation notation? Because it's kind of hard to say, well, it's 0 if x, coefficient is 0 if x is even, and it's this weird 1 over something factorial with a plus or minus sign if x is odd. But we've already seen that we can encode the odd numbers with something like 2n plus 1. So if I do something like this, x to the 2n plus 1, and we actually know we're dividing by 2n plus the same number, right? So the same number factorial, and there's a plus or minus, and if I stick in minus 1 to the n here and start at n equals 0, you can check. If you can check that if you write out the first few terms of this, like this would be the n, well, this would be the n equals 0 term right here. This would be the n equals 1, right? If you plug in n equals 0 to this formula, you can check. You'll get x to the 1st over 1 factorial minus 1 to the 0 is positive 1, so you'll get x. And you can check if you plug in n equals 1, you'll get this term with the minus sign and stuff. You should sort of check a few of these very explicitly to make sure that you see it. So sometimes won't be every power of x won't be appearing, but there's usually some pattern and some way we can write it and put it in summation notation. So, okay, I'll stop there and do more examples, more involved examples.